In this video, we're going to look at section 1.2, which is all about inductive and deductive reasoning. So we're going to start off by just looking at each of those definitions. So inductive reasoning is the process of drawing a general conclusion by observing a pattern in specific instances. And the conclusion that is drawn from inductive reasoning is what we call a hypothesis or a conjecture. So that's what we refer to the conclusion as, either a hypothesis or a conjecture. We also have what's called deductive reasoning. So deductive reasoning is where we're using accepted facts and general principles to arrive at a specific conclusion. So notice inductive reasoning said that we are drawing conclusions by observing a pattern in specific instances, whereas inductive reasoning, we're using these already accepted facts and general principles to make our conclusion. So we have a few different scenarios we're going to look at where we're trying to identify, is the given scenario one that would require us to use inductive reasoning or deductive reasoning? And then we're going to get into some examples of building on that and applying that knowledge to actually solve some different problems or analyze some different patterns. So the first example, we've got parts A, B, C, and D. And so what we want to do here is just very simply identify the reasoning process that would be used to work through this problem. So we're just identifying, would we use inductive reasoning or deductive reasoning? And we want to explain our reasoning. Very important on that part. So the first example says that we examined the fingerprints of 2,083 people. No two individuals in this group have identical fingerprints. We conclude that for all people, no two people have identical fingerprints. So we are making our conclusion based off of the information that we've collected from the fingerprints of these 2,083 people. So what that means is we're drawing our general conclusion from the observations in these specific 2,083 instances. So this scenario is one where we would use inductive reasoning. Okay, so we said a general conclusion is being made from repeated observations of specific examples. The second scenario says every coach must know his sport well. Marty Wright is a baseball coach, so Marty Wright knows baseball well. Now in this scenario, we don't have any type of pattern or specific instances that we're focusing on. We start by just saying, well, every coach knows his sport well. That's a pretty broad and pretty general assumption that any coach is going to be very versed in their sport. So it's that very broadly accepted fact. So we're using that fact that because coaches know their sport and because this particular person, Marty, happens to be a coach, then he will know baseball well. That is deductive reasoning. So we have general principles here. that are being applied to specific examples. Our third situation says if the mechanic says that it will take 7 days to repair your SUV, then it'll actually take 10 days. If the mechanic says, I figure it'll take 1 week to fix, ma'am, then you can expect it to be ready 10 days from now. Okay, so again, this is kind of a general broad assumption, right? That overview of if the mechanic says this. So this is once again a deductive reasoning situation. And so we can use the same explanation we used on the last one, that we have general principles that are being used or being applied to specific examples. Okay, so the last one we have of this type is part D. You read the newspaper daily. Lately, you have noticed more articles about increased tuition at various public and private colleges and universities. You draw the conclusion that all colleges and universities have increased tuition. So, you're reading the paper, you're reading it every single day over and over and over again. So, the conclusion that you draw is based on that pattern, those specific instances that you are repeatedly over and over again going through that paper. You're able to make that conclusion that tuition is increased. So this is an example of inductive reasoning. And so we would say, similar explanation as we had for part A, that a general conclusion is being made from repeated observations of specific examples. All right, so we have gone through different situations where we are trying to classify a situation as inductive or deductive reasoning. So what we are going to do now is just look at different examples and situations where we have to actually apply that knowledge in some way, shape, or form. So the example we have tells us in 1742, Christian Goldbach made the conjecture, he made that hypothesis, that we could write every even integer greater than 2 as the sum of 2 prime numbers. Now, it says not necessarily different, so it could be the same prime number that we're using. Well, what is a prime number? A prime number is a number like 2, 3, 5, 7 that can only be divided by 1 in itself. So we want to illustrate this conjecture by taking the even integers of 20, 48, and 100 and writing them as the sum of 2 prime numbers. So that's our task. Okay. So let's think about each of these numbers. So we've got 20. We've got 48, and we've got 100. So we said prime numbers are numbers that can only be divided by 1 in itself. So if we were to look up or kind of go through our different numbers to generate that list of prime numbers. We have the first few given to us, 2, 3, 5, 7. If we were to continue that list, the next prime number we would find would be 11, and then 13, then 17, 19, 23, 29, and so on. So we're looking for two of these numbers that we could take and add together to equal 20. And so there could be a couple of different combinations to satisfy this. Okay, looking at what we have, I noticed that we could use 3 and 17. So 3 plus 17, that would equal 20. If I wanted 48, like we said, if we were to continue, extend our list of primes, we would find, we notice 11 is a prime, but we would also find that 37 is also a prime number. So 11 plus 37 equals 48. And for 100, we could use the prime numbers of 41 and 59. Okay, so like we said, if we were to list out, continue going through, now we said a prime number means if I'm trying to divide it by something, the only number I can divide it by is itself and 1. So we want to keep that in mind as we're searching for those prime numbers. Okay. We also have instances where we're going to need to use inductive and deductive reasoning for patterns, for sequences. So that's what we want to use here. In those, we're using our inductive reasoning because we're looking at those observations and those patterns. So we want to use our inductive reasoning to predict the next term in the sequence. So if we look at part A, we go from 5 to 12 to 19 to 26 to 33. So we're looking for some type of common pattern here. So how did we get from 5 to 12? Well, 5 plus 7 gives us 12. Okay. How do we get from 12 to 19? Well, that's also just adding 7. 19 to 26, add 7. So it does appear, let's see, 26 plus 7 is 33. So our pattern is adding 7 here. So then to figure out the next term, we would just need to take 33, add 7, and that would give us 40. So that would be the number that goes in the blank for part A. Part B, 3 to 9, okay, we can add 6. But if we think about that, to get from 9 to 27, adding 6 does not work. So maybe we're thinking about another pattern or another trend that's going on here. Well, we said we could get from 3 to 9 by adding 6. We could also get there by multiplying by 3, though. Okay, 9 times 3 also gives us 27. 27 times 3 gives us 81. 81 times 3 gives us 243. So in this case, our pattern is multiplying by 3. So then we have 243 times 3. When we multiply that, we will get 729 for the next term that goes in the blank. Okay. And the last one we have for part C, we have 1, 1, 2, 4, 7, 13, 24, 44, and 81. So at first glance, this one doesn't have a very clear pattern, consistent pattern like part A and part B. So this one's really going to make us dig deep and really tap into that inductive reasoning. So what we notice is after a little bit of analyzing, a little bit of really just thinking through it, if we take 4, how do we get 4? Well, we can kind of use the numbers that come before it in that pattern. So specifically, if we take 1 plus 1 plus 2. 1 plus 1 is 2. 2 plus 2 is 4. So we're using the 3 terms that are in front of it. Let's see if maybe that could give us a starting point. So if we take 7, is 7 equal to the 3 terms that are in front of it? So that would be 1 plus 2, which would be 3, plus 4, which would be 7. Okay, so with this one, it's a little bit different, but our pattern is going to be the sum of the previous 3 terms. So what that means is to figure out what comes next, we're going to have to take 24 plus 44 plus 81, and that will give us the value that is next in this sequence. And that number ends up being 149. So we have 149. Okay. So sometimes we're going to have to just really sit and think on these a minute in order to find that pattern. And we might have to try some things before we get to our final solution. Okay, so we have 2 other scenarios or types of problems we see in this section. The next one is looking at a magic square. So a magic square is similar to, the way I think about it is Sudoku puzzles. Okay, so there's some similarities there with the skills that you need to use in order to effectively solve those properly. Now, a magic square has more stipulations than just a regular Sudoku puzzle, but a magic square is just a square arrangement of numbers, and the conditions are if you add the numbers in any row, column, or diagonal, you're always going to get the same sum. Now, the magic square uses every single number, all of the integers from 1 to 16 exactly one time. So in this case, we're not using our inductive reasoning. There's no pattern to it. We're going to use that deductive reasoning instead to try to fill in the boxes to satisfy all of the conditions here. So we have 3 parts here. We are going to determine the total of all the numbers in the square. We're going to determine the total for each row, column, and diagonal, and then we are going to actually complete the magic square. So if we start with part A here, so part A and part B are going to be the same for both of these magic squares. Okay. But if we look at part A, we said you have to use every single integer from 1 to 16 one time. So because all of those numbers will be in one of the boxes in the magic square, if we want to find the total of all numbers, then that means we're going to just very simply do 1 plus 2 plus 3 plus 4 all the way to 14, 15, and 16. So we're going to add all of those together. 1, 2, 3, 4, 5, 6, and so on. So once we add all of those together, we find that the total all together in that entire square is going to equal 136. So we have that piece figured out. Now for part B, we need to figure out the total for each row, column, and diagonal. So this one might require us to take a little bit longer thinking it through. But what's super important to recognize here is if you're looking at the total for a row, the total for a column, and the total for a diagonal, if they all have to be the exact same value, then what that allows us to do is take our grand total that's going to be in this box, that 136, and it's going to have to be distributed evenly. It's going to have to be shared. It's going to have to be the same value no matter if you're going from left to right, top to bottom, down the diagonal. And so in each of those instances, you're splitting that up between 4 boxes. So what we are able to do here is take our 136, divide it by 4, and that gives us a value of 34, which is exactly what every single row, column, and diagonal should add up to. So now that we know that, we can start using the missing numbers to fill in our magic square. So if we look at the first one, we can either start in the very bottom row or the very right column. So in the very bottom row, we have 4, 1, and 14. We're missing a number, but whatever we put there has to make that entire row add up to 34. Okay, so if we take the numbers that we currently have and add them together, that would give us 19. So then that means we need one number to make it to 34, so it's going to be 15. Okay. On the far right column, we have 9, 8, and 14. Currently, those 3 combine to equal 31, so we need 3 to make it equal 34. Now that we filled that in, we can fill in the second row from the bottom. 13, 3, and 2. The missing number that we need there is going to be 16. Okay. And then from there, we could fill in on the far left column. We could do that one. We've got 7, 13, and 4. So that's 24, so we need 10. We can do the diagonal, 7, 2, and 14. We need 11. Now that we filled that in, going across 10, 11, and 8, we need 5. And then the last 2 values we end up needing 6 right there and 12 right there. And now we have successfully completed that magic square. Okay. So what I want you to do now is pause the video for a minute or two, take a second, and see if you can manage to fill in the second magic square on your own. Okay, and then resume this video to see if you have all of the values correct. Okay, so these are the values that you should have gotten for that second magic square. Okay. This one did require you to think a little bit more as you got closer to the end. There were a few values that you kind of just had to test in the appropriate box, but this should be that final completed magic square. So the last problem that we have here is more of an ordering type of problem. So if we look at this, we've got 4 students. Adriana, Caleb, Ethan, and Juliana. They're traveling to a conference to give presentations. So we want to use the given clues to determine who is giving which speech. Now notice it tells us we need to be systematic in this approach. So we want to think about our orderings that we talked about in section 1 in class last week. Okay. So we have 4 individuals, Adriana, Caleb, Ethan, Julia. We have 4 presentations: recycling, solar power, water conservation, political issues. Our information, if we start with the first one, says Julia will be speaking before the speech on water conservation, but after the speech on political issues. Using that information, we can kind of go through and mark out some of these boxes in this table to narrow down our options and help us figure out who is giving which speech. So Julia is going to be speaking before water conservation. So she is not doing water conservation. She is also not doing political issues, okay, because she's speaking after political issues. The speaker on solar power helped Ethan and Julia make their presentations. So if they helped both of those people make those presentations, that means it's not either one of them. So the speaker on solar power is not Ethan and not Julia. So we immediately see that means Julia has to be our speaker for recycling. So I'm going to put a little check mark there. Ethan is speaking last. Okay, he is not interested in political issues. Okay, so Ethan's not doing political issues. So, but we also know actually in solidifying the fact that Julia is doing recycling, nobody else is going to speak on recycling. So that means Ethan must be speaking on water conservation. Our last clue, our last piece of information is Caleb will be speaking after Julia. Okay? Might not seem very helpful at first, but let's think on that for a second. We did say Ethan was doing water conservation, so that means Adriana and Caleb are not. Okay, we are down to our final two, and we're trying to figure out, is Adriana doing solar power or is Caleb doing solar power? This is where the be systematic approach is going to help us, because if we just look at this as it is, we're left with a 50-50 chance on choosing the right person for the right speech. But remember, with the systematic approach, that's when we're analyzing everything in its proper order. So, if we think about this, if we think about the big piece of all this information we haven't really analyzed yet, there have been little hints sprinkled in, little pieces of information about order. Who is speaking when? Who is speaking before and after? So, if we think about this, Ethan is speaking last. So Ethan has to be last. Okay. Let's see. Julia is speaking before water conservation and after political issues. So that means she can't be first. She's either second or third. Okay. But we also notice Caleb has to speak after Julia. So that means Julia has got to be second. And then if Caleb is speaking after her, he's got to be third. And so because of that, that means Adriana would have to be first to go. So kind of going through that, we said Ethan is last. Caleb's after Julia. Julia has a speech before and a speech after. So that is where we're going to be able to nail this down and figure out which one, Adriana or Caleb, is giving the solar power or the political issue speech. And it all ties back here. Julia is before water conservation and after political issues. So let's look at who's before. That would be Miss Adriana. So Miss Adriana being before, or I'm sorry, Adriana is before Julia, but that means that is the speech on political issues because Julia is going after that person. So that means Adriana is doing the speech on political issues, and then Julia is before water conservation. So Julia is before Caleb, which means Caleb has to be water conservation. So that means we have our final answer. Okay, so that was section 1.2, inductive and deductive reasoning.